Welcome to our study modeling the global potential of smart farming innovations.
Agriculture. We know the total food demand is expected to increase by around 50% in 2025. And at the same time, we know the risks of pesticide pollution increasing all over the world. At the same time, the critical N surplus, nitrogen surplus is increasing and it's very high in some regions of the world. Also, the growing water stress in cropland is becoming a problem. We also know that declining agricultural labor supply over time is also a potential problem for future. Smart farming innovations, often referred as fourth industrial revolution in agriculture, which includes advances in sensing and robotics and artificial intelligence. Some innovations are at development and diffusion stage, and some are already established, such as GPS steering assistance system, precision agricultural tools, and early stage technologies such as autonomous weeding machines or autonomous irrigation system. The unifying element of this smart farming innovation is the reduction of input waste, substantial reduction in environmental pollution, and increased yield. This study has main three objectives. First, producing global map where in the world each smart farming innovation has its greatest potential. Secondly, we make first attempt to link the potential of smart farming innovations to address specific sustainability challenges to the global occurrence. And third, we simulate future scenarios assuming continuing economic development. For collecting data, we started our global survey by asking questions to the researchers, companies, and farmers. Why, where in the world farmers use the following technologies and it is profitable for them, following by some other questions. Then we use our survey data as a training data, and then on top of that we add economic factors, infrastructural factors, environmental factors, policy factors, demographic factors, and use special machine learning techniques, random forest, generalized linear model, support vector machine, maximum entropy, and gradient boosting machine. And then we ensemble all the output from different models. Here we use special 5K fold cross validation for the accuracy, and then we got our desired map. Result here. Here we see the global potential of all innovations. A is showing where in the world application mapping for precision agriculture has greatest potentials, and other map is showing the rest of the technologies. Here we mostly see in Europe and in USA and also Australia, Japan, New Zealand, these areas, all of the innovations has huge potentials. But in China, India, and somewhere else, we found that precision agriculture has a high potential, but for weeding machines and GPS steering assistance system doesn't shows a high potential in Asia or Africa or even South America. There is a hope and an expectation that smart farming can play an important role to address pressing sustainability challenges such as biodiversity loss, water stress, and agrochemical pollutions. Overlying the potential of selected smart farming innovations with grand sustainability challenges, we see some interesting pattern. For this research, we matched the general potential of all smart farming innovations with global pattern of biodiversity loss. In figure A, the potential of smart irrigation system and a map of global water stress in figure B, the potential of variable rate technology and fertilizer pollution or agricultural nitrogen pollution in figure C, and the potential of semi-automated weeding machines and pesticide pollution in figure D. Area with high rates of biodiversity loss and also high potential of possible technology solutions are especially indicated, for example, for North and South America, Western Europe, South Africa, China, Australia in figure A. This also applicable most for other innovations as well and other sustainability challenges. A naturally arising question is how future economic development might affect the potential of smart farming innovations. To explore this, we simulated a scenario with 50% increase in Human Development Index. So in this figure, you see specifically a yellow and green color. So yellow color where profitability or potentials stable before and after the simulation, and the green color means where the potentials increased after increasing HDI. As is clearly visible, this has more of an effect for some innovations and in some regions than others. For example, variable rate technology became considerably more profitable on average at the global level, whereas the impact of GPS steering assistance system is much more limited. Also for autonomous weeding machines, the potentials increased in USA after increasing HDI, not everywhere in the world. In short, we found in the large region of the world, there is already farmers for whom these innovations are profitable or has huge potential. This can be expected to expand considerably, and also in many regions, there is potential that these technologies can contribute to achieving sustainability development goals. The data was the main limitations of this research, and we think this research has huge policy and research implications. Thank you. Thank you.